Hi. We didn't have time in the two lectures this week to discuss a small concept that comes up in many places. So I just want to indicate what is the relevant definition and what is the most important behavior that you have to think about for that. So subset metrics. Suppose we have a metric space XD. Now you can build other metric spaces by taking subsets of this space. And if we have a subset, how we define a new distance, sometimes this is indicate D is restricted to A. It's defined, so if we have 2 points in A, we define its distance as being the distance in the original space X. So example, if we have the unit circle, sometimes denoted S1, consisting of all the points x, y with x squared plus y squared is equal to 1. This is a subset of the plane. And the subset metric, D restricted to S1, is just the metric from the ambient space. So in particular, if we want to look at the distance restricted to S between the point 1, 0 and minus 1, 0, this would be 2. This is the so-called distance as the crow flies, because this would be the diameter of this ball. Now there is another distance on the circle. That would be the distance that you have to actually travel if you are in this subset, the so-called path distance, and that would be bigger. So this is a different distance than that so-called path distance on the space. It's just the restriction of the distance from the big function. Now, if we define that distance, and sometimes I will just drop this notation because the distance function is the same. We just construe it as having a different domain as just x, y, and a. So for now, after this, I will just drop that extra baggage and keep in mind that the domain is different. So if I take a ball in with respect to dA, centered at x and radius r, and if x is in a and r is positive, well, what is this? This consists of all the points y, but this time this is a ball in A. So all the points y such that distance in A between x and y is at most r. But the distance in A is just the restriction of the distance in x. So this consists of all the points in A such that distance between them in the ambient space is at most r. And this is the same thing as saying that you take all the points in x whose distance is at most r, intersected with A. So points that are in A and in this ball, and this is the same thing as BX R, the ball in the ambient space, intersected with E. So what we get from this is useful inequality that balls in the space in the subset are intersections of balls in the big space. Now, let's do so the definition is fairly natural, but there are some weird things that happen that are a little counterintuitive until you get used to them. So suppose my subset A is 0, union 1, 2, and this is a subset of R. Then 0 as a subset of A is open in the restricted metric dA. Now, 0 as a singleton is not open. 0 as a subset of R is not open. So depending on what you are a subset of and what is the context, then openness is different. So this claim, I won't prove that 0 is not an open set in R. This you can prove by just using the definition. If you apply, let's take a small ball of radius R, it will contain points that are not equal to 0. That's fairly automatic. But it is an open subset in the restricted metric. And why is this? Well, we have to show that there exists a delta positive. So for every point, for every x in our omega, we have to prove that there exists a delta positive such that if we take the ball in our restricted metric, centered at our x, radius delta, this is contained in A. Well, our set is a singleton, so there's only one point to check. Let x is equal to the 0, the only point. We have to choose an epsilon delta that works, and we'll keep in mind what we just argued, that the intersection of the ball is an intersection, is itself a ball in the restricted metric. So let's pick delta equals 1/2, and then by above, BDA centered at 0 of radius 1/2 is equal to the ball of radius 1/2 centered at 0 intersected with A. But this is our set, so this easily can be seen as being just the singleton 0. And well, this is equal to omega, and omega is also a subset of itself, so it's a subset of omega. So we get that the dA ball of radius 1/2 is a subset of our set omega. So the singleton equals that is an open set. So the restricted distance has different open subsets than the whole thing. Now, using similar reasoning, one could show that also 1, 2, if we define another set omega 2, this is an open set in A. Similar. And this is a good exercise. So even though it's a closed interval, then in this different metric space, namely A with the restricted distance, this set becomes open. And this way, the ideas of open and closed, they start to be a little in divergence of what we mean by elsewhere, but they satisfy the definitions of open and closed. And in some ways, there are still aspects of openness that are holding here, because this point, still everything in its complement is far away from it. So that property of openness is still shared. And if we take this point, this set, then everything outside of it, namely just 0, is quite far away from it. So there's a little bit of room in terms of distance between them. There's just no elements that fit in between. And that's where the difference with our usual notion of openness and closeness comes in. Now, one can actually characterize open subsets. So if we have a subset of A, which is itself a subset of X, then omega is open in D with respect to dA, the restricted metric. If and only if there exists an open set of X such that omega is the intersection of A with that open set. So we saw that balls are intersection of balls. Similarly, open sets are intersections of open sets. So this proof has two directions. Suppose omega subset of A is open in dA, and we want to conclude the conclusion. So we want to find a V. Now this is a little bit tricky, but we can combine facts that we have proven in other places, other videos. So it's open in dA. That means that for every point in omega, there exists a delta such that if we take the dA ball centered at delta, which is equal by above to the delta ball intersected with A, that this is contained in omega. So let's now, for each x in omega, choose a delta x positive such that bx delta x intersect A is a subset of omega. This is possible by what we just said, but this requires infinitely many choices. Now define, and this is the hardest part of the proof, define V as the union over all the points in omega of the ball Bx delta x. Now this is a huge union because the set omega can be very large, but it just means those points that belong into one of these balls. So this is our set V. It is a union of open sets, of open balls, which are open in the usual sense. So V is open. And because so V is open, now next, V intersected with A is equal to the union over x in omega. We take the intersection of the balls with A. Now each one of these is contained in omega, so the entire union is contained in omega. So we know that this is a subset of omega. On the other hand, if x is in omega, then x belongs to bx delta x, and this is contained in the union because this contains all the points that belong in some of these, and this is equal to V. So x is in V for all x in omega. Also, x is in A because omega is a subset of A. And what we get from this is that every element of x is an element of omega and x. So we get that x is inside, well, it's an element of V and an element of A. So it's an element of V intersect A. In other words, what we just showed is that omega is a subset of V intersect A. And before that, we showed that V intersect A is a subset of omega. And from these, we can conclude that omega is equal to V intersect A. And we're done for the one direction. from the first claim to the second claim. This is if and only if. So we have to do the other direction. It's a little bit easier. Suppose omega is equal to V intersected with A, where V is open. Well, we have to verify that omega is open in the restricted metric. Pick an x inside omega, and our task is to find a delta, since the delta ball is contained in omega. Well, x belongs into V, so since V is open, there exists a delta positive such that Bx delta in the big space is contained in V. So now if we take Bx delta intersected with A, this is contained in V intersected with A. But this is the same thing as B dA x delta. And what we get, this is the same as omega. So we get that with that choice of delta, B dA x delta is contained in omega by same choice of delta. Delta positive, and this is done because we found a delta that works. So this is the proof that subsets in a subset that are open with respect to the relative topology are just intersections of open sets. One could prove similarly that a subset C of A of X is closed if and only if there exists a closed subset of X such that K is equal to, that C is equal to A intersect K. But to show this, it's better to talk a little bit about topology, and this will be done in a separate video.